Hi, hello, welcome back to my channel Civilka ADDA. So those who have not subscribed to my channel, please do subscribe to my channel. So in this video, I would like to explain about the design procedure of singly reinforced beam. So how to find the singly reinforcement beam, so that I would like to explain. So complete design procedure. So watch the video till the end. So moving to the first step in the design procedure of singly reinforced beam, so we need to find the cross-sectional dimensions. So we need to find the cross-sectional dimensions. So the depth of the beam is fixed based on span by depth ratio. So based on span by depth ratio, we are going to take the ratios. So we'll see that. So to satisfy the deflection requirement, so you can refer the page 37 IS 456-2000. So you'll be knowing what are the various span by depth ratios for different cantilever or simply supported or continuous. So let me show that. So basic values of span to depth ratios for spans up to 10 meters. So for cantilever it is 7, for simply supported it is 20, for continuous beam it is 26. So the page 37 IS 456-2000. So after finding the effective depth D is equals to span by depth. So see here, so span range, loading and span by depth ratio. So for 3 to 4 meters, so if loading is light, so then you can take the span by depth ratios as 15 to 20. So if 5 to 10 meters span range, so if it is medium to heavy load, so you can take 12 to 15 L by D ratio. So if it is greater than 10 meters, so if the loading is heavy, so then you can take the span by depth ratio 12. So after finding that, so you need to find the effective length, right? So effective length is equals to clear span plus effective depth. So we have two ways to find the effective span. So that is clear span plus effective depth and clear span plus center to center support. So whichever is less, that you can adopt. So adopt the less value among these two. So this is the first one and this is the second one. So which value you are getting less, that value you need to take is as the effective span. L is equals to that many meters. So after finding the effective depth and effective span, so the next step is how to find the loads. So the self weight is equals to area of the section into unit weight of RCC. So we are going to take the area of the section, what is given in the question, that area. So B into D into unit weight of RCC. So that is 25 kilonewton per meter cube. So that you are going to take. And imposed or live load is equals to dash kilonewton per meter square. So total load dash kilonewton per meter square. So this you need to find out, and the self weight, that is dead load plus live load, will give the total load. Then after getting the load, you need to calculate the design load. So this is the working load only, actual load only. So to find the design load or factored load, WU, it is given by partial safety factor into W. So whatever you have calculated partial safety factor into W, that will give the PSF. So design load W is equals to partial safety factor into W. So W, whatever we have calculated just in previous step, so that into 1.5, the partial safety factor will give the factored load. So after finding the loads, you need to find the ultimate moment and shear force. So till now what we have seen, so how to find the effective depth, how to find the effective span, then after that loads. So then ultimate moment and shear force. So ultimate moment mu is equals to WL square by 8. So if it is simply supported UDL, so then shear force VU is equals to WUL by 2, right? So we need to find out the ultimate moment and shear force. So after finding that, moving to the tension reinforcement. So tension reinforcement based on the grade of steel given in the question, that is Fe 250 or Fe 415 or Fe 500, based on that you need to take the mu limit equation. So if it is Fe 250 0.149 FCK BD square and Fe 415 0.138 FCK BD square and mu limit for Fe 500 is 0.133 FCK BD square. So based on the grades of steel. So after that, you need to compare whether it is balanced section or under reinforced section or over reinforced section. So if it is mu is equal to mu limit, then it is a balanced section. So mu is less than mu limit, then it is under reinforced section. So if it is mu is greater than mu limit, then it is a over reinforced section. So after finding that, you need to find the moment of resistance. So mu is given by 0.87 FIAST D into 1 minus FIAST by FCK BD. So in page 96 IS 456 2000. So based on this formula, we are going to calculate the required steel. So how much area of steel is required? So in tension reinforcement, that you are going to find out. So after finding that, so how much is provided? So minimum AST provided. So minimum AST provided as per IS 456 2000 clause number 26.5.1.1, which is in page 47. So it is AST minimum is equals to 0.85 BD by Fy. So substitute all the values and you will be getting the AST minimum. So cross check with the AST required. So then provide it. So the diameter of hanger bars should not be less than of 10 mm and that of main bars 12 mm. So this is note. So normal diameters of bars are like 8 mm, 10 mm, 12 mm, 16 mm, 20, 25, 32 mm, right? So for hanger bars it should not be less than 10 mm. For main bars it should not be less than 12 mm. So after that you need to find the number of bars based on the AST. So number of bars is equals to capital AST by small AST. So capital AST, the AST is tension reinforcement what we have calculated, and small AST is the based on the assumed diameter of the bar you need to find out. So pi d square by 4 like that. So assume the diameter, so based on the previous step. So like this, all different bars. So you can assume any one bar and then substitute it and you'll be getting the AST number of bars. So number of bars into pi d square by 4 will give the AST provided. So that you need to calculate. So after that you need to find out whatever we have calculated is satisfying or not. You need to cross check it. So after getting the number of bars and diameter of the bars, so it is that we have designed complete beam. So we have designed the single reinforcement beam, but you need to check whatever we have calculated is satisfying the requirements or not for shear and deflection. That you need to calculate. So nominal shear stress tau C is equals to VU by BD. So it is there in page 72, clause number 40.1 in IS 456 2000. So this formula is there. So VU already we have calculated in the previous step. So VU by BD will give the tau C. So then you need to find out. So this is tau V. So you need to find out the tau C value. So to get the tau C value, you want the percentage of tension reinforcement. So this tau C values will be taken from the table 19, which is in page 73. So after finding that, you need to compare the tau V is less than or greater than the tau C. So let me show this table 19. So these are the table 19. Based on the percentage of steel, we are going to calculate, and based on the concrete grade. So you are going to take it. So if we have given M20 grade concrete, so you have to take these values based on the PT values, 100 AST by BD. So if you want detail about this, I have already solved and I have already did the video. I'll link it at the end of the video. So after that, we need to cross check for deflection control also. So here PT you need to find based on the PT value whatever we have calculated. So deflection control is L by D max is equals to L by D basics into KT into KC into KF. So I'll show that also. Figure 4, 5 and 6. So see here. So L by D max is equals to L by D basic. So Fs values, you can take this Fs formula from page 38. So 0.58 into Fi into AST required by AST provided. I'll show that also. See here. In page 38 IS 456 2000. So this is the KT value modification factor. So 0.58 Fi into area of cross section of steel required by area of cross section of steel provided. So modification factor for tension reinforcement and percentage compression reinforcement and reduction factors for ratios of span to depth ratios for flanged beams. So you need to see and you need to take the values. So these are in page number 38 and 39. So just now I have shown. So L by D max is greater than L by D provided. So then it is safe against deflection control. So if it is in shear stress, if tau V is less than tau C, then it is safe against the shear stress also. So whatever we have calculated, whatever we have designed the complete beam, that should satisfy this. So that is check for shear stress and check for deflection control. So thank you for watching the video till the end. If you like the video, please like, share and comment the Civilka ADDA and subscribe to Civilka ADDA.